Oh, it didn't come on. Why, thank you. I tried to turn it on, but somehow I failed. Perhaps this? Ah, there we are. Good, thanks for telling me. All right, so, all right, we're here in CNET 127. Time to talk about format string bugs, and it's time to start demonstrating some of the Linux projects. So, we'll start with format strings, and that goes here, although a lot of this is going to be demos. So, we talked before about format strings, and the fundamental problem, which we're going to be exploiting all through this course, is that computers do not understand context. You have data, it's just a series of bytes, and it could be an integer, a video, a picture, part of a string, machine language instruction. It's all just a series of bytes, and the same series of bytes can be interpreted in different ways. That's the fundamental problem here. So, when you print something in a C program, if you print out a variable, like you define a variable I as 1001, when you print it, you can print it different ways. %d will print it as a decimal, %5d will print it as a decimal 5 characters long, %x will print it as hexadecimal, and you could print it other ways too. So here you have a string, %c will print it as a character, %s will print it as a string, and here you have a pointer, %p, and so there's various things here. So let me run this one live. I should have it all ready to go here. CH4. All right, and this is an Intel-based machine I'm connecting to over the cloud. All right, and that one should be format 1. Let's take a look. All right, I guess I didn't bother with all these different versions. Let's take a look at this one here. So %d is here, 1001. Here's one with an extra space in front of it to make it 5 characters long. That's the 5d. Here's %x, and here's %5x, where it adds a couple spaces in front. 3e9 is 1001. If you've been doing the binary games, you should understand that. This is 9 times 1 plus 14 times 16 plus 3 times 256. So it's almost 400, which would be 1024. It's 1001. 1024 minus a little bit. So here's a string. You define a H10, a character array that can hold 10 characters, and then you copy the word hello into it. So now I have hello, and when I print out the character, here, A is 65, that's a capital A, and the string is hello. So the character format string is %c, and %s is the string format string. A pointer is %p, so there I can print out h, which is the pointer to the start of this array. And if I just print %x, %x, %x with format strings only and no variables, surprisingly, C does not consider this to be an error. It will compile and run, and it will print data. And so the question is, what is this data? I didn't tell it what variable to print, and it printed out some data, so where did that data come from? And that's what we're going to talk about here. So the most important formats that we care about are %x for hexadecimal, and with a number in front of it, so you can control the length. Those are the main ones we're going to use. So, for format strings vulnerabilities, here is the fundamental problem with C. It does stupid things, like here I define an array that can hold 10 characters. Then I copy in something with more 10 characters. You couldn't do this in Visual Basic or Java or Rust. It would either give you an error message or it would automatically make the array bigger to make enough room for it. But C will just do it. So when you do the string copy, it will just take the start of this array and copy byte by byte starting there as much as you want, without noticing that it's gone off the end. That's why the stir copy routine is one of 10 similar functions that are considered too dangerous to use these days because they tend to cause buffer overflows. So if you have a print like this, can I explain hex? Yes? Let me bring up the this thing here. Hexadecimal, you have, if you write down a 15, that if you write down 10, you call it A, and 11, you call it B. This is hex. And you go on down to 15, and that's F. So one character, so you have the characters 0, 1, 2 to F, stand for the numbers from 0, 1, 2 to 15. And that is 4 bits. So 4 bits of binary, this is a nibble, equals 4 bits. So bytes are 8 bits, and that is 2 nibbles. So the bytes 0, 1, up to 255 encode in hex as 0, 1, up to FF. FF is the largest possible hexadecimal byte, and this stands for a series of 8 ones that are bits. And so the pattern is, if you have hexadecimal, the character on the right is the number of ones, and the next character to the left is the number of 16s, and if you have a 3-digit number, like 400, that means 4 times 256 plus 0 times 16 plus 0 times 1. And if you want to practice these things and see a more complete explanation of them, you'll find them here in the binary games, the early project here, which, whoops, I thought it had it in here. Maybe I don't have it in this class. Thought I did. It's in my other classes. If you go to 121, it's in there. Projects there. Here's some binary games. I'll put them in the chat if you want to do that explain this stuff step by step. And it's a good thing to know if you want to understand binary numbers. Anyway, so here, if you print with nothing, there's no arguments to print. Logically, this should just give you an error message saying you didn't give the arguments, but instead, C just pulls 4 values from the stack and prints them out. So this is an information disclosure vulnerability. This command prints data which was not supposed to be visible. So that's, I think, what I've got here. If I do ed204.c on my server, let me clear. Okay, let's do all right, so this one is going to take a string from the user. Let's see, I think I have a simpler one to start from. I don't know why it's not in my examples there. Let's look at format 1. All right, this one has a number 1001 and it just prints it as a decimal. So if I run that one, I see the number in 1001. Now if I look at this program called format 2, this time I print it, and then I add this line, %x n, with nothing. So if I run that one, I get this, and I get those extra numbers. And so this printing random numbers, by the way, as I just mentioned, this 3E9 is in fact 1001. So the first one it printed equaled this number, but the others are strange other numbers we haven't seen. So let's try this other program, ed204.c from a project, and this one reads a line, a command parameter argument. You can name of the program, and it reads in argc. You have to have a string, and that is argv0. argv0 tells you how many arguments there are. argv0 is the number of the program. Oh boy, I'm getting it all wrong. This is the name of the program. When you want to take command line arguments in C, you put this stuff in, int argc, *** argv, and now argv0 is the name of the program, and argv1 is the first parameter. So I put that in a buffer, and then I print the buffer. That's all that's going to happen. It will print whatever I give it as a command line argument as the buffer. So if I give it no command line argument, it will tell me that's no good. You have to provide a string. And if I give it a %x, it will print a strange random value. And I could give it a series of %x's, and I'm getting a lot of random data. All right, so that's showing I'm able to dump some data here, and if I do this, if I put something on the stack, like 4 A's, then notice here 41, 41, 41, 41. That's hexadecimal for the letter A. So these A's I put in are in fact on the stack somewhere, and I can find out where they are. I can also put dots in here just to make it easier to read, to separate things. And now I can see that if I put a 32-bit value here, that value will appear 4 characters down on the stack. So I can control things that appear here. All right, and the last one that's fun is %n. %n will crash the box with a segmentation fault. So let's talk about why that happened. So this is what we got there. And here's the explanation. This will read 4 words from the stack. %n is a bizarre format string which writes to memory. It takes the value of the variable, interprets that as an address, and it writes into that memory location. I don't know why you would ever want to do this. But therefore, if I just write to random locations, then I'm very likely to write to a random location that is not allocated for the use of this program, and that's why I get a segmentation fault. It tried to write to this address here. In this case, it tried to write to this address. AAAA is the first thing it's going to find, I think. Anyway, it tried to write to some random location, some one of these numbers, and it was not a valid memory location. So, all right. Now, the actual value it writes is equal to the number of characters printed so far. So I assume the original purpose of this is somehow to format something so you can print it. But the end result is you can really take over the box with it. So we can write to arbitrary RAM locations, and that's an easy denial of service. We could corrupt memory in a variety of ways, and therefore we can gain code execution if we figure out a good place to write to. And these are caused by this whole series of functions that cause these format string vulnerabilities. All these versions of printf use a format string, and it will allow you to print with a format string without specifying the variable, and that's what leads to this problem. So you can prevent this. By the way, stack defenses will not stop it. Things like a canary value to stop the buffer from overflowing, and address-based layout randomization, and non-executable memory to stop you from executing code you injected will not stop this attack because I'm not injecting any code, and I'm not overflowing a buffer. Static code analysis tools could find it. You could easily find it yourself with just a text editor and search for the print statements and see which print statement doesn't have a comma inside there, that sort of thing. Just looking at the source code with a code analysis tool should find it. GCC, the compiler, will warn you, but it will not prevent this. So here's the exploitation technique, and we'll do this. So a format string gives you the ability to write to a memory location. So now how do you take over the box with a write? Well, you have to find a target RAM location that will eventually be used to determine the EIP, and then you can control the EIP. So you write 4 bytes to the target RAM location, insert shellcode after it, find the shellcode, and write the shellcode address to the target RAM location so it executes the shellcode you've injected. So the end result is very much like the classic buffer overflow, but you're doing it through a format string. So as I already showed you, if you just put 4 characters here and then some %x's, you can find out where they went. So by the way, in case you think it's a coincidence, that one there, I could do this. I could change the AAAA to 1, 2, 3, 4. And put the X back at the end. All right. And you see, if I put an AAAA here, it appears as the 4th parameter. And if I put a 1, 2, 3, 4 here, that also appears as the 4th parameter. Notice that 31 is the numeral 1. This is ASCII. 31 stands for numeral 1, and 41 stands for the letter A in ASCII. And I'll just bring this up in case people don't know about this ASCII table. That's how ASCII works. In hexadecimal, 31 is number 1, 32 is number 2, and 41 is a capital A. So those are good ones to know. And so whatever 4 bytes I put here will appear 4 words down in the memory. So I can control it, and I know what I'm controlling. Now, if I go back to here, all right. And sometimes, for some programs, it's much further down, like the 300th character. So actually finding where it is on the stack can be quite a chore. But for this simple program, the stack frame is very small, so you don't have to look very far. And if you look in the assembly code to call a function, you'll see why this works, which I think we have coming up. Let me just take a look. Yeah, we're going to see how this works. But let me just do this right now while it's on my mind. If you want to know why this works when you print it, you can look at how it's called. If I GDB this program, ED 204, all right, and now I list. All right, this calls, it's just main is the one. Let's see if I do list 1 to 20. All right, so here is the part that causes the flaw. And that is in the main routine, and I just want to see how that's called. So I disassemble main. All right, and I look down here, here's the printf. And notice this is a normal printf. You push the variable you're going to print on the stack, and then you call printf. So that's an appropriate, and up here you push another thing. So first you push the variable you're going to print, then you push a pointer to the format string, then you call printf. That's how it works. But if you go down to the next one, down here, it does only one push before it does a call. It pushes the format string on the stack, and then it calls printf, but it did not push the variables here. So when printf is entered, it will just look on the stack, and whatever it finds on the stack, it will assume you pushed that there. This is the problem with C. C is just the easiest way to write assembly code. So when you call a function, the function does not know if you actually prepared the arguments correctly. It just runs on the data it finds on the stack, assuming you must have set it up correctly. Just like when you do a string copy, it just copies those bytes into that memory location, and it does not check to see that you allocated enough space to hold what data you're putting there. C just assumes that you are a clever programmer and you thought of all this, which is why it causes all these problems, because the programmer has the responsibility to think about what could go wrong when this function is executed, and that's a heavy intellectual burden, and most programmers are not good enough to be careful enough to avoid that. So, so you have to find somewhere to write in memory that will take over the instruction pointer. And one thing you can do is find a saved return address on the stack, and then when something returns, you can do it. That's one way to do it. But an easier thing to do is to use the global offset table, which is what we're going to do. The global offset table is a table of values that point to the C library functions. And so you can change one of the functions to do something else. There's also a destructors table that's called when a program exits. You can change that, and then when the program exits, it'll go to the address you choose. And there are other C library hooks. So there's also something called the @exit structure, which points to something when you exit a routine. All right, so here, as we just did, if you disassemble main, you'll see first it calls printf, and then it calls exit. You see that here. Here is the last printf, the one it didn't prepare for properly, and then it's going to call exit down here. So if I change the meaning of the C library function exit, it will call that after this is done. I can change this address, and then it'll call the code I injected instead of the code the developer chose. So that's an easy way to do it. And in order to do that, I have to find the global offset table entry for exit. And you do that with objdump -r. Objdump lets you see what's inside an executable, and -r shows you the relocation records. So I put in my executable name, and here you see this very simple program does not use very many functions. It uses printf, stir copy, exit, and putchar. So here's where exit is. So the pointer to exit is at this location, 804A014. So if I write to that location, I will change the location of exit. And when my program tries to call the exit C library function, it will instead go to the data I put in there. So we're going to do that in GDB. So I run this program in GDB. All right. And now I'm going to examine that point with x, 1x. I can look at the global offset table, 0x, 0804, A0, 14. All right, that is the pointer to exit. See, it's labeled there, and it's pointing, this is the actual address of another pointer, which points to the C library function exit. But if I write to this memory location, it will change. And in order to write to that memory location, I have to give it those 4 bytes, and then %x, 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 %n. Now this may be confusing, but here's how it works. Remember before, when we ran this function, I'm going to just scroll back to it. When we ran this function right here, you run the program, the first 4 bytes you appear here, they appear as the 4th value on the stack. So that AAAA appears here. So if I put the 4 bytes of the address I want to write to here, and I then give it %x, 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 %n, it will print out these 3 values, and it will write to that memory location, which is this location. So I found this very confusing when I first learned about format string attacks. But you put an address here, you put in a few %x's to pad it, and you put a %n there, and it will write to that location. So that's the attack here. The attack is run, and I have to run with literal text, which I can do with $apostrophe. Now I put in the address I want to write to, which is 14A0, XA0. You have to put it in reverse byte order, as we talked about before. 0804. 0408. Okay, that is the start of it. And now I need %x, 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 %n. So now I need %x. I need to skip the next 3 bytes on the stack and then write to the 4th byte, which is going to contain this value. And now, when I do that, the program crashes, and it ended up with this in the instruction pointer. And if I look at that relocation record, now it contains 0001B. So that is that's what happened. By putting in the address I wanted to write to there, then 3 %x's and a %n, I wrote to there. Why am I writing to the 4th byte? It's writing a 32-bit value. So it's not writing just that 1 byte. It wrote this entire 32-bit value. And the 32-bit value it wrote was the total number of characters I printed so far. And the total number of characters is this 1B, which is a small number. It's about 30 or 28. That's just the total number of characters here. So that's why the actual value written is the number of characters I printed, and the location you write to is the 32-bit word there. So that's the deal. So here's Python code to write 1 byte, and I should have that here. If I quit, all right, let's see what I've got. That's probably F1. Yeah, I wrote it in Python 3 here. So this is the Python 3 code to write 1 byte. No, I guess this one's writing 4 bytes. So I don't think I wrote the one that did 1 byte. But here is just writing that. You have the pointer to it here, and then you have the format, and then you just print those out. This is Python 2. In Python 3, the code looks a little different. But then you could run /f1.py. You could take the output of that program to run it instead of having to type it in literally. So let's go on to the one that relies 4 bytes, because that's more the point. Now, I've got the one that does 4 bytes here. What I do now is, I could do it all with 1 write, but I might have to write up to like 4 billion characters, because 2 to the 32 is 4 billion. So to make an arbitrary 32-bit number, I would have to print 4 billion characters, and that's ridiculous. So what I do is I print 4 times. First to location 14, then 15, then 16, then 17. And so what that does is it's going to do this. If you consider, I'll have, say, 4 values I want to write to here. All right. And let me put the address down here. So I can have an address ending in 14, and then 15, and then 16, and 17, and then some other ones after it, and then say 20. All right. So when I do the first write operation targeting 14, it's going to put some data here and here. And when I do the second operation, it's going to put data here. And the third one is going to put data here. the fourth one is going to put data here. And remember that Intel is little endian. So that means the least significant numbers are here and the most significant numbers are here. So if I put in a small number where the higher order bytes are all 0, all I need is to print up to 256 characters to get a length I want here, to make this 1 byte what I want. So by 4 write operations, I can write the bytes one by one until I have put exactly the right value I want here. And by the way, I've done some collateral damage. I've changed 3 other bytes here to zeros in the process, but I just don't care. It's going to mess up some other global offset table entry or something, but I just don't care about that. So 4 write operations targeting 4 memory addresses incrementing by 1 will do to write an arbitrary 32-bit word. And I will only have to write a maximum of 4 times 256 characters or so to do that. So that's what this does. Now the first one does not control what value is written there. It just puts this, it writes the first 4 words, and then it prints the format, and the format will do %x, 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 %n, %x, %n, %x, %n, %x, %n. So there are 4 %n's in there, and those target these values here. The junk value is in between them. And so I will do 4 write operations when I write this one operation. So if I run this program, f1.py, it prints out these unprintable characters, and then the word junk, and then all the format strings there. So if I run this in a debugger, gdb -q, let's see what's going on here. All right, ed204. All right, now I'm going to run taking data from that program, which is F1, yeah. All right. And now it crashes with this location, 37, 3F, 47, 4F, and I can check it by doing that examine, which I did up here, which was this one. This is looking at the global offset entry. So you can see, of course, this is where the exit should be, but instead of pointing to the real function, it now has 37, 30F, 47, 40F. And this is the 4 write operations in that order, and so it had printed 37 characters at this point, and then 3 F characters by that point, and then 47 and 4 F. So those are the number of characters printed so far. So I have now filled all 32 bits of that address with stupid junk, which caused the program to crash. So that's the first attack. Now I want to put a chosen value there. So let's look at that one. That's going to be my format 2. I'm going to make a second window here so I can view the Python code All right, now let's go into 127 and chapter 4. Okay, and now I'm going to cat f2.py. All right, so this time I'm using Python 3. I import the system library. I define those 4 addresses I want to write to. Then I define the values I want to put there, AA, BB, CC, and DD, just to get something to do. And then I took, the first time I did this, I took the value that I saw here, which was 29 at that point. Now it's 37. So anyway, I have 29 plus 7 is what I used here in hex. I just did it by trial and error. When I ran the program that I developed on a previous system for an earlier semester, it was off by 7, so I just added another -7. I just determined this by trial and error. This is basically how many characters were written before you started doing the writing to memory. And so this will now take 256 characters plus more to add up to this, and this is 256 times 2, 256 times 3, and 256 times 4, so each one of these is long enough to do it. That's what's going on. And then it will just print these 4 characters. And this junk here is what you have to do to encode arbitrary bytes for printing in Python 3. It's a little harder than it was in Python 2. But anyway, this is the thing that will now target AABBCCDD. So if I run that one over here, which is F2, and start from the beginning, now I do end up with AABBCCDD in the instruction pointer. So, and I can check it by looking at that offset value, and that's what I put there. Now it's still crashing because that's not a valid memory location, but now I'm controlling it. Now all I have to do is choose a better location to put in there. And, all right, and for that, I'm going to put in dummy shellcode, so that's the next one here. Let's go to the window that's outside GDB and clear and cat F3. All right. Yep, here we go. So this is all the same. The 4 addresses you write to, the starting values I'm going to write there. And now, I'm not going to change these yet. Now I'm going to insert more stuff over here. After I put in the addresses and the format strings, which write to memory, I'm just going to put a NOP sled and shellcode right there on the stack after all that. Now I've injected it somewhere in memory, and if I can figure out where it is, I can write that address. The NOP sled is 190s, which are no operation, and the shellcode is just going to be 250 CCs, which are breaks. That's just a place to put shellcode. So this is still just the outline, the framework of an attack. But I'm seeing if I can do it all and if it's going to work. So when I run this one, it's going to load up memory that way. Now when I run this one, I want to use a break command. I'm going to view the stack in GDB. I thought I might have to put a breakpoint in to do that. Let me go back and see. Nope. I might just be able to see it when it crashes. We'll see. I don't remember whether I have to have a breakpoint or not. So let's just try it. That's going to be here. All right. So now I run with F3. Yes. Now it crashes, but I think if I do info register, okay, there's a stack frame that goes from D06C to 488. So if I examine the stack, that'll be like X450X ESP. And I remember this number, the stack ends at 488, although in fact that's not as important as it is in a buffer overflow exploit. So now, if I rearrange my window so it fits, I see, here's the NOP sled, 90, 90, 90. And if I look at the next page, here's the fake shellcode. So I have found where the NOP sled is. The NOP sled goes from there up to there. So I know what address to put in. It would be any address you find here. Any address in that range that doesn't have zeros in it. So just picking an address in the middle, if I inject an address like that, that would be a way to make an attack work, something in that area. Then when it goes to exit, it will jump here and it will execute NOP, 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 and then hit the break. And I'll see that it's working. So this is the next thing to try. And that's what I should have in the other window here. If I clear and cat F4. There. Now, I took that address here. The one I found before was FFFFD0FC. And as you can see, D0FC is fine. There's that address. It hits one of the NOPs. So I want to go to that address instead of AABBCCDD. So I put that here in reverse byte order, FFFFD0FC. And now, instead of crashing, it should run and hit the breakpoint. So let's see if this one works. I just give it, okay. Now I want to run it with F4. Yes. And see, it ends with a breakpoint trap, which is very good. It didn't crash. It hit a logical breakpoint. If I do info registers, the EIP is at that location, FFFFD125, and I can see what's going on by looking, I can, for example, one way to do it is to look on the stack directly, ESP, and just remember that number. The EIP is D125, and so here's the NOP sled, and here's D125 is in this line, that's D125. So it slid down the NOPS and hit that. There's another interesting way to see it, by the way, in GDB, which is to examine 10 machine language instructions starting at EIP minus 5. That should do it. And now you'll see NOP, 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 and I hit the first int 3, and that's where I am. It executed this int 3 and stopped. So you can see the code. So now I know that the exploit is, now I know I can find the code I injected, and I know I can execute the code, which means that the stack is executable here, which is a parameter I had to define when compiling this code. But that's the point. So now that I can do that, I can execute code I put in there. So now the next thing you have to do is make sure that there are no bad characters. Remember, as you inject code, you're injecting this stuff into a string, and so things that terminate the string will break your shellcode, like null bytes will almost always break your shellcode, and often tab, line feed, carriage return, and space will also break your shellcode. It'll be interpreted by the program as the end of the string. So you have to check and see if those are in there. So I made a bad character program here. And there it is, bad.py. So this one will, I left all this alone, and here it's going to print these characters. It's going to just take all the bytes from 1 to 255, except for 9, 10, 13, and 32, and 0. I didn't include 0. So I think all those are bad. I'm going to put all other characters here and inject that. That's what I'm going to use for my shellcode. And the point is, I'm just putting in those bytes to see if they get there. If any of those bytes terminate the string, then the bytes after them will not make it in. So if I run this one on bad, run bad, all right. Now I just examine the stack the same way we did before. It crashed, of course, because I didn't inject any real runnable shellcode this time. But all I care about is to see what's going on in the stack. So here's the 90s, and here's the stuff I injected. 1, 2, 3, 4, 5, 6, 7, 8. I skipped 9 and 10 because those were like carriage return and line feed, then B, C, D, E, F, and so on. So you see all these characters, 44, 54, 64, 74. And the point is, it goes all the way up to A, B, and here's C, D, E, F4, and F9, FC, FD, E, F there. So all the characters got in there right up to FF. So I have found all the bad characters. It was just those 5 I didn't include here. So I now know that I can inject any byte except those 5. So I can use shellcode as long as it does not use a null or any of these characters. So to make that, Metasploit has this ability. MSF Venom can do this. You can generate shellcode with this command. You tell it what exploit you want to do, and I'm doing a shell bind TCP that will just make a listening shell for incoming connections on port 4444 by default, and then I have a -B, and I list the characters to avoid. Null byte, 9, A, D, and 20. And then this prepend fork just made it run better. It's something about make a new process when you spawn the shellcode, and I want it in Python. So when I do that, I get Python code buff that I can use, and I've already done that for my demo here. So if I go here, that will be F5. All right, and so the F5, all this part is exactly the same as before. I'm going to write to those 4 bytes to control the pointer to the exit function. This number is the same as before, so it will hit my NOP sled, and the NOP sled is the same as before, 190s, but now I define this thing called buff, which I just copied and pasted from Metasploit. This is the binary code that will make a listening shell, avoiding the 5 bad bytes. And then I make padding to make the total length 250, because you always want to make your exploit have constant length, which is not really necessary here, but it's a good general practice. And now I write that out. The 4 words that are going to control the addresses to write to, the format strings that are going to include the %ends that do the writing, the NOP sled, which is just a series of NOPs just to make my exploit easier to write, this buffer that came from Metasploit, and then just some padding. So if I run that one, that is F5. And run it. Now, it did a fork and exited normally, so it didn't crash at all. It didn't get interrupted. It forked to launch a new process, and one of the processes exited normally. And if I do ss -pent to see socket state in TCP on this machine, I now am listening on port 4444. So it did launch a shell, and I can connect to that shell with a netcat 127.0.0.1, port 4444, and now I can do things like ID, ifconfig. I can execute commands. I don't see a prompt, but I do see the output of the command. I can do who am I? You know, I can do various things. I've connected to that shell. So Control C will terminate and get me out of there. And that should close the shell. That'll break the network connection, so no longer is listening on 4444. So that is the whole process of exploiting something with a format string vulnerability. And it's all the same as what you did with a buffer overflow vulnerability, except you didn't have control of the EIP directly. You had to go find that global offset table value to write to. So that's my shell. All right. And I've got some Kahoots about this, and then projects to demonstrate. So here's the Kahoot. Yes, those code examples are all in the project. What I just did was basically a demonstration of this project. I'll point it out after the Kahoots. ED204, though, you saw the name go by. The step-by-step instructions to do it are there, and you'll be doing it for homework. All right, I'll wait a few more seconds, but this might be all we're going to have. All right. So, what does %d mean? A number to print in decimal, that's what the D stands for. The ordinary number, the way you usually print them. All right, what about %n? Yep, that's the one that writes to RAM. All right. All right, how about %p? That's a pointer. All right. All right, so how do you stop format string exploits? And none of those defenses will stop this attack. You just have to review the source code. All right. All right, and which one of these is used when a program exits? Yeah, the destructors is used at the end of a program, always. Now, you could use the global offset table if you actually call the function exit, but you don't have to call the function exit. You can just end the program, and then it will still use the detours. It's another place you can put data that will end up in the EIP. All right, so the winners are Sid, okay, Jose, all right, so let me stop this and stop this recording.